Hey everyone, and welcome back for another deep dive. Today we're going to be exploring something that's pretty mind-boggling.
Yeah,
It's called the Planck scale.
absolutely.
And it's basically like this threshold where our current understanding of physics just kind of like falls apart.
It breaks down, yeah.
Yeah, and we're going to be looking at some excerpts,
Right.
research about the Planck scale.
Yeah.
So get ready for some really
scale.
crazy concepts.
Yeah, it's really interesting because I think what's really cool about the Planck scale is that it's not just like some,
Right.
Yeah.
Good.
arbitrary idea.
Right.
It's actually defined by these fundamental constants of nature.
Yeah.
Named after
Max Planck,
Max Planck. That's right.
the revolutionary himself.
Quantum revolutionary, yeah.
So we're talking about a set of units here
Yeah.
that describe like the most extreme limits
Exactly.
of the physical world.
Yeah. Yeah, we're talking about 5 key units here. Planck length, Planck time, Planck mass, Planck energy, and Planck temperature.
All right, so let's try to like wrap our heads around this.
Okay.
I'm trying to imagine like the Planck length,
Okay.
but it's just so
It's tiny.
impossibly small.
Yeah.
Like, is there a way we can even like compare that
Absolutely.
to something?
So imagine if you took our entire observable universe,
Okay.
and shrunk it down to the size of an atom. The Planck length would be like the width of a human hair compared to that atom.
Wow, that is just
Yeah.
unfathomable.
That's incredibly small.
So if we were to like zoom in to that level,
Right. What would time even?
would time even make sense?
Yeah, so that brings us to Planck time,
Okay.
which is about 5.4 times 10 to the power of medical 44 seconds.
Oh, wow.
So to put that into perspective, that's the time it takes for light to travel a single Planck length.
Oh, wow. Okay.
So it's considered like the smallest meaningful unit of time.
Right.
And yeah, at that level, our perception of time would be totally different.
Totally.
Yeah.
It makes you wonder if time even exists at that scale,
Right.
you know,
It might not.
as we experience it.
Totally different, yeah.
What about the other
Yeah.
Planck units like mass energy
Yeah.
and temperature? What makes them so special?
Yeah, so think of those as kind of like the boundaries of reality as we know it.
Okay.
Planck energy, for example, is about 1.22 times 10 to the power of 19 giga-electron volts.
Wow.
So that's an energy level so high that we believe gravity itself becomes quantized.
Quantized gravity. So
Yeah.
gravity,
Yeah.
the force that holds the universe together,
Yeah.
starts acting like little packets of energy.
Exactly.
But
So you see, in the quantum world,
okay.
energy doesn't flow smoothly like a ramp. It kind of jumps in these discrete steps,
Okay.
like climbing a staircase. And at the Planck scale, we believe gravity might behave this way too,
Wow.
which leads us to kind of the biggest challenge in physics,
Yeah.
the quest for a unified theory of quantum gravity.
So we have quantum mechanics,
Right.
which describes like the bizarre world of particles.
Yeah, exactly, the subatomic world.
And then we have general relativity,
Right.
which explains gravity on this cosmic scale.
On these large scales.
But it seems like at the Planck scale,
They clash, yeah.
yeah, that's the heart of the problem.
Right.
These two fundamental theories that work so beautifully in their own separate domains,
Yeah.
they just seem incompatible at this incredibly small scale.
Right.
And that's why physicists are tirelessly searching for this unified theory, this quantum gravity,
Yeah.
that could bridge that gap between the very large and the very small.
So it's like these Planck units kind of mark
Yeah.
the boundaries of what we know.
Absolutely.
But what's so fascinating is that scientists are actually conducting research. They are.
At this level,
Yeah.
how do you even begin to study something?
It's really hard.
That's so
Yeah.
unbelievably tiny.
So that's what makes these recent discoveries in the field so extraordinary.
Yeah, right.
Like, for example, there's a team
Yeah.
at Aix-Marseille University and the Institute for Quantum Optics and Quantum Information.
Wow.
They're working on this mind-blowing project.
Okay.
They're trying to detect Planck-scale dark matter using quantum interference.
Hold on. So they're trying to use like the principles of quantum mechanics,
Right.
the science of the extremely small
Yeah.
to find dark matter,
Uh-huh.
which seems like this vast cosmic enigma.
It might sound counterintuitive,
Yeah.
but the idea is that even though dark matter doesn't interact much with ordinary matter,
Right.
it still exerts a gravitational influence, even
No.
at the Planck scale.
Okay.
So what they're looking for are these tiny shifts in quantum systems,
Right.
like subtle ripples in a pond, that could reveal the presence of these elusive dark matter particles.
Some seriously
It is.
genius thinking.
Uh-huh.
Like using the most delicate instruments
Right.
to probe the biggest mysteries of the universe.
It really is.
But here's the thing.
Yeah.
If our current theories
Yeah.
break down at the Planck scale,
Mm-hmm.
how can we even make sense
Right.
of any findings?
That's where these new mathematical frameworks come in.
Okay.
So researchers are developing these tools to kind of redefine
Right.
fundamental physical properties like mass and charge
Okay.
using this Planck scale formalism.
Right.
Think of it like creating a new language
Okay.
to describe the universe at this fundamental level.
So it's not just about
Yeah.
observing the Planck scale.
Right.
It's about creating new ways
Exactly.
to understand it.
Yeah, we need new tools.
It's like realizing there's a whole other layer
Yeah,
of reality beneath what we
absolutely.
really perceive.
Yeah.
This deep dive's already getting deep.
Yeah,
It is.
yeah, it is.
But I'm definitely hooked.
And remember the Planck satellite that mapped the cosmic microwave background,
Right?
which is basically a baby picture of the universe from just after the Big Bang.
Yeah.
And it provided this incredible support for the standard model of cosmology.
Right.
But it also revealed some curious features
Right.
that we're still trying to understand.
You're talking about like that
Yeah.
mysterious cold
It's
spot.
a cold spot, yeah.
Yeah. That's always fascinating me.
Yeah.
Some people even suggest that it might be evidence of other universes.
That's one of the hypotheses, yeah.
Is there a connection between that
Right.
and the Planck scale?
It's certainly possible. So some physicists believe that these anomalies in the cosmic microwave background
Okay.
could be like echoes of these quantum gravitational effects from the very early universe.
Yeah.
A time when the Planck scale was dominant.
So I'm starting to see how the Planck scale connects to
Yeah, it connects to everything.
so many different
It really
areas
does.
of physics
Yeah.
and cosmology.
Hmm.
But before we dive even deeper,
Yeah.
I'm curious to hear more
Okay.
about those new mathematical frameworks that you mentioned.
Mm-hmm.
What exactly are they, and
Yeah.
how could they change our
Yeah.
understanding of the universe?
Yeah. So these new mathematical frameworks are really fascinating.
Yeah.
They're basically attempts to rewrite the rules of physics
Okay.
in a way that's compatible with both quantum mechanics and general relativity.
Right.
One approach that's gaining a lot of attention is something called loop quantum gravity.
Loop quantum gravity.
Yeah. Have you heard of that?
I have, yeah.
So the basic idea
Yeah, what's
is to imagine
basic idea?
the fabric of space-time
Okay.
as a finely woven tapestry.
Right.
But instead of threads, it's made up of these tiny loops of energy.
Okay.
And these loops are incredibly small, on the order of the Planck length. And loop quantum gravity suggests that space-time itself is quantized,
Okay.
meaning it exists in these discrete chunks rather than a smooth continuum.
So instead of space-time being like a smooth sheet, it's
Huh.
more like a
Yeah.
chainmail armor.
I love that analogy. Yeah, it's like a chainmail armor made up of these interconnected,
The loops are constantly
interacting.
and
It's not
evolving, giving
evolving.
rise to the dynamic nature of space-time and gravity.
Okay, so that's a pretty,
It is a pretty mind-bending.
yeah, mind-bending
Like,
picture, but I think I'm
Yeah.
starting to get it.
Okay, good.
So how does this all connect to the Planck scale?
Well, the size of these loops is directly related to the Planck length.
Okay.
So in loop quantum gravity, the Planck scale isn't just a limit.
Right.
It's the fundamental building block of space-time itself.
So it's like the Planck scale is the
Yep.
pixel size of reality.
That's a great way to put it.
That's pretty wild.
It is pretty wild.
So what about those other
Yeah.
frameworks you mentioned?
Right. So another promising approach is string theory.
String theory, yeah.
Yeah, you've probably heard of that.
I have, yeah.
So string theory suggests that the fundamental building blocks of the universe aren't point-like particles,
Okay.
but these tiny vibrating strings.
All right.
And these strings can vibrate at different frequencies.
Right.
And these vibrations determine the properties of particles like mass and charge.
String theory always seems so abstract to me.
Yeah, it can be.
How does it relate to the Planck scale
Okay.
and this whole idea of quantum gravity?
So string theory naturally incorporates gravity,
Okay.
and it operates at the Planck scale.
Right.
And one of the really interesting things about string theory is that it predicts extra spatial dimensions
Okay.
beyond the three that we experience.
Right. Length, width, and height.
Exactly, length, width, and height.
Yeah.
But string theory says there are more,
Okay.
But these extra dimensions are curled up and hidden.
At incredibly small scales, close to the Planck length.
Okay.
Think of it like looking at a garden hose from afar.
Okay.
It appears one-dimensional,
Right.
but up close you can see its circular dimension as well.
So it's like these extra dimensions are like the circular dimension of the garden hose,
Yeah.
but curled up at the Planck scale.
That's a great way to visualize it.
That's crazy.
It's wild.
But if they're so small,
yeah.
how can we even detect them?
Right, so that's one of the biggest challenges in string theory.
Right.
Some physicists believe that high-energy experiments, like those conducted at the Large Hadron Collider, might be able to produce particles that hint at the existence of these extra dimensions.
Okay.
Others believe we might see indirect evidence in the cosmic microwave background radiation.
Wow, so we're talking about using giant particle accelerators
We are.
and telescopes to look for clues about these tiny curled up
It's connecting the largest scales of the universe
to the smallest.
It's amazing how scientists can connect the largest scales of the universe to the smallest.
That's pretty awesome.
But what are the practical implications of all this?
Right.
Like, why should we even care about these theoretical frameworks and the Planck scale?
But it's not just about abstract physics.
Okay.
These theories have the potential to revolutionize our understanding of the universe and lead to new technologies.
Okay.
Imagine harnessing the power of quantum gravity to create new forms of energy or develop advanced communication systems that exploit extra dimensions.
That sounds like something straight out of science fiction.
Yeah.
But it's exciting to think about.
It is.
What are some of the biggest unanswered questions that these theories are trying to address?
So one of the biggest mysteries is the nature of dark energy.
Dark energy, yeah.
This mysterious force that's causing the expansion of the universe to accelerate.
Right. And some physicists believe that understanding quantum gravity and the Planck scale could provide insights into the origin and nature of dark energy.
So by delving into the smallest scale of reality, we might unlock the secrets behind the largest scale.
It's possible,
Phenomenon we know.
It's all connected.
The accelerating expansion.
Exactly. The universe is full of surprises.
That's pretty wild.
It is wild.
Speaking of the vast universe, we've been talking a lot about the incredibly small.
We have.
But earlier we touched on black holes.
Yes.
Which are some of the most massive and mysterious objects in the universe. How does the Planck scale play into our understanding of black holes?
So that's a great question. At the heart of a black hole, according to the Einstein's theory of general relativity, lies a singularity. A point of infinite density and zero volume. And that's where our current understanding of physics completely breaks down.
So a black hole singularity is like the ultimate Planck scale environment.
You could say that, The conditions at a singularity are thought to be so extreme that quantum gravity effects become dominant.
Wow.
It's like the laws of physics as we know them get rewritten at the singularity.
That's fascinating.
It's mind-boggling.
So to understand black holes fully, we need a theory that can bridge the gap between general relativity and quantum mechanics.
Exactly.
A theory that works at the Planck scale.
That's the key.
And that's why understanding the Planck scale is so crucial.
It is.
It might hold the key to unlocking the secrets of black holes.
It might.
Which in turn could illuminate our understanding of gravity.
Gravity, space, and time.
And time. It's like a cosmic puzzle. Where the smallest pieces hold the key to understanding the grandest picture.
This is truly mind-boggling.
It is.
And to think we've only just begun to explore the mysteries of the Planck scale. We're just scratching the surface.
It's a reminder that there's so much more to discover about the universe.
Absolutely.
And the fundamental laws that govern it.
For sure.
Absolutely.
Yeah, and as we continue to probe deeper into the Planck scale, we're likely to uncover even more surprising and counterintuitive insights that could reshape our understanding of reality itself.
It's like we're embarking on a journey. That could lead us to a completely new perspective on the universe and our place within it.
I agree.
Well, I'm definitely ready to continue this journey.
Okay.
What other mind-bending concepts await us as we delve further into the Planck scale? So we've been talking about all these like incredible theoretical frameworks and mind-blowing concepts. But I have to ask, given how like inconceivably small the Planck scale is, will we ever be able to like directly observe it?
That's the question, isn't it?
Or experiment at that level?
Yeah.
Is that even
Yeah, that's the million-dollar question.
within the realm of possibility?
And it's really tough to say for sure.
Yeah.
The energies required to probe the Planck scale directly are just far beyond anything we can achieve with current technology.
Yeah.
It would be like trying to build a skyscraper using only grains of sand.
So does that mean we're stuck with just theoretical models and indirect observations?
Not necessarily.
Okay.
There are some really clever ideas being explored.
Right.
Some scientists are looking at ways to use astronomical observations as a kind of cosmic microscope.
Interesting.
So, for example, by studying tiny distortions in the cosmic microwave background, that faint echo of the Big Bang, we might be able to glean indirect clues about Planck scale physics.
It's like using the entire universe as a giant laboratory.
The universe is our laboratory.
And there are other intriguing avenues, too, like quantum computing.
Oh, yeah.
Is advancing at an incredible pace.
Right.
Some researchers believe that one day, quantum computers might be powerful enough to simulate quantum gravity effects.
That would be amazing.
So that would be revolutionary.
It would open up a whole new world of understanding.
But even if we can't directly observe it, why is understanding the Planck scale so important? Why should we even care?
Good question.
About what happens at these unimaginable scales?
Because it's about understanding the very essence of reality itself.
Wow.
Like, think about it.
Yeah.
The Planck scale is where gravity, the force that shapes the cosmos, meets the quantum world, the realm of the very small.
Right.
Understanding how these two realms intertwine could lead to a complete transformation of our understanding of everything.
Yeah.
From the birth of the universe to the nature of time and space.
It's like we're trying to piece together the ultimate cosmic puzzle.
Yeah.
And the Planck scale holds the key.
It does.
It's connecting all the pieces.
It's the missing link.
And who knows what amazing insights and breakthroughs await us.
Who knows?
As we delve deeper into this extraordinary realm.
Yeah, maybe we'll discover completely new particles or forces that we never even imagined.
Or maybe we'll find a way to unify all the fundamental forces of nature into a single elegant theory.
Wouldn't that be amazing?
Yeah.
The theory of everything?
Or maybe, just maybe.
Oh, maybe.
We'll unlock the secrets to, like, traveling through time.
Okay, now you're venturing into the realm of science fiction.
Or warping space-time itself.
Yeah. But hey, who knows what the future holds?
Right.
The point is, exploring the Planck scale isn't just about abstract physics.
Right.
It's about pushing the boundaries of human knowledge and understanding our place in this vastness of the cosmos.
Absolutely.
And that's something we should all be excited about.
I couldn't agree more.
Yeah.
This has been an incredible journey.
It has.
Into the Planck scale.
Yeah.
From the unimaginably small to the incredibly vast.
I know. It's amazing how those two things are connected.
We've covered everything from quantum gravity and dark matter to black holes and the cosmic microwave background.
We've covered a lot of ground.
But I think what stayed with me the most is this sense of wonder and possibility that this topic evokes.
Yeah, it really makes you think.
It's a powerful reminder that there's still so much out there to discover.
Oh, for sure.
And the journey of exploration is just beginning.
Absolutely. We're just getting started.
Well said.
Yeah.
And who knows, maybe someday.
Yeah.
Thanks to the brilliant minds working on this very problem. We'll be having a completely different conversation about what we've learned at the Planck scale.
Exactly.
A conversation that could reshape our entire understanding of the universe.
It could change everything.
And everything in it.
Yeah.
That's a thought-provoking idea that will definitely stay with me.
Yeah.
So to all our listeners out there,
keep
your minds open, your curiosity alive, and never stop exploring the wonders of the universe.
The universe is an amazing place.
And remember, sometimes the biggest discoveries come from exploring the smallest scales.
That's right.
Until next time.
Yeah.
Keep diving deep.
Keep exploring.